Alrighty, hello everyone. In this video, we're going to be looking at molecules that have carbon-carbon single bonds or sigma bonds. We're going to look at what happens if we rotate around that carbon-carbon single bond. Okay, so let's take an example, right? So methane, ethane, propane, butane. So we have this hydrocarbon molecule that only has carbon and hydrogen bonds, right? And remember, it's drawn in this case as a line bond structure where every end and every corner is a carbon atom. And if you think about a neutral carbon atom, it's in group 4A, has 4 bonding electrons. So a carbon atom with 4 bonds has no charge and is neutral. So when we draw the structure as a line bond structure, every end and every corner is reflecting a carbon atom, but we don't draw hydrogens attached to carbon. So if we take a look at this carbon atom, for instance, it has 2 bonds on paper. That means it must have 2 more bonds to hydrogen atoms. All right, well, what we're interested on in the moment is to actually what happens if we rotate around that carbon-carbon single bond. So what about if I take this carbon-carbon single bond and I rotate the molecule? Right? Then I might get something that looks like this. Okay, well, what if I take this and I rotate the molecule this way? Then I'll get a molecule that looks like this. Are those 3 different molecules any different? Are they considered constitutional isomers? Remember, constitutional isomers refer to molecules that have the same exact chemical formula but are connected differently. They're not, right? We can go with the longest carbon chain, look at substituents, it's exactly the same. And if you name it exactly the same way, then it's exactly the same molecule. So what we call those are different conformations. Right? And you can get different conformations within the molecule through bond rotation, right? I'm going to say, so what we have is sigma bond rotation. Rotation. All we did is we rotated around a sigma bond or a single bond, right? So let's take an example, or let's take look at a molecule. All right, so here is a carbon-carbon single bond. Right, let's just make sure my mic is on. Here's a carbon-carbon single bond, and we can rotate around a carbon-carbon single bond, whether we're rotating around this carbon-carbon single bond, and then one group of the molecule will move, or the other group around that carbon-carbon single bond would move. If we're rotating around this carbon-carbon single bond, we can rotate and this group moves, or we can rotate and this group will move, right? So we're looking around simple rotations, bond rotations, that gives us different conformations of the same exact molecule, right? But what we typically do when we look at different conformations is we look down a specific carbon-carbon bond. We're looking down this carbon-carbon bond, for instance, right? So I'm just going to make it into the same molecule, right? So think about all of those being hydrogen atoms, right? Think about them being hydrogen atoms. So this is very much like this molecule, this is very much like this molecule, and then this is very much like this molecule, just different conformations. All right, so suppose this is what you start off with, and what you're doing is looking down this carbon-carbon bond. And you're seeing how whatever groups are attached to either carbon, how they're affected through this bond rotation, all right? This bond rotation, whether it's the front carbon, this carbon, whether it's that carbon. And what we do is we look down that carbon-carbon bond. So if you take a look, it looks like there's only a single carbon atom if you look straight down at it, all right? So what you do is think about it as you're rotating. So this is what you have, and then you are rotating it 60 degrees, another 60 degrees, another 60 degrees. So that's like 180 degrees from the point that you started off with. And then you can go another 60 degrees, another 60 degrees, and then another 60 degrees. You're back 180 degrees later, back to the point that you started off with. Or you could be rotating the back carbon, right? You could be rotating the back carbon 60 degrees, another 60 degrees, another 60 degrees, right? So we could think about it in terms of the overall energetics of the molecule. So think about it in terms of the potential energy, the position or associated with that molecule. Would you expect, so if we could think also about it in terms of those two being the bulkier groups, whereas those two, which in this case are just reflecting hydrogens, for our purpose, they're less bulky. Would you expect the molecule to be more stable if the bulkier groups are farther apart, or if the bulkier groups are closer to one another? All right, so we're going to talk about what we call Newman projections. All right, so Newman projections allow us to see the different conformations across a carbon-carbon bond, whichever carbon-carbon bond we may be interested in within that particular molecule, right? So I'm going to draw an example. All right, so again, methane, ethane, propane, butane. But to explain Newman projections better, instead of just keeping this carbon attached to two hydrogens, I'm going to attach other groups to it, right? So I'm going to go ahead and form a bond to bromine, a bond to an alcohol group, a bond to chlorine, and I'll do another alcohol group, right? So now when we're looking at rotation, we're either rotating, think about it as you're looking down this carbon-carbon bond, and you're looking how whatever groups are attached to this carbon or that carbon, how they're affected when you're actually rotating, right? And is it rotating the front carbon, whatever is attached to the front carbon, or the back carbon? Very similar to what we saw a moment ago, right? Are we rotating the front carbon, or are we rotating around the back carbon? Okay, so what we're really doing is looking down this carbon-carbon bond, okay? And when we draw a Newman projection, we think about whichever direction, whichever way we're looking. So suppose we're looking down this carbon-carbon bond, and our eyes are looking straight down this carbon-carbon bond. So the bond, like the way we're looking is through this carbon, and this is what we call our back carbon, right? So when we draw a Newman projection, we have to draw it in such a way to reflect that, right? So the back carbons are really the circle. This circle reflects the back carbon. And then there's four groups attached to it, right? There's one group that is in plane of the paper, right? And there's two groups that are on dashes and wedges. And if you recall, a wedge is pointing outside of the plane of the paper and towards you, whereas a dash is pointing behind the plane of the paper and away from you. All right, so this reflects this back carbon, right? It could be looking like this. It could also be where this group is pointing downwards instead, and it looks like that. Or it could be anything in between, right? This is like a 180-degree rotation, but it could be anything in between as well, and we could think about that as the back carbon atom, right? It's the back carbon atom, right? This is our back carbon atom, and those are the three different groups that are attached to it. So if this is our back carbon, we have an alcohol, a chlorine, and a methyl group. All right, and then we have to consider the front carbon, but our front carbon, we simply draw it looking like this, or looking like that, and that's really our front carbon atom. Our front carbon atom. All right, so that's our front carbon atom right here. Right, our front carbon, that's our front carbon. All right, and in Newman projection, we're really putting this on top of that, or this on top of this, or this on top of that, or anything in between. All right. So how do we draw something as a Newman projection, right? The very first step is to decide which side are you looking at it, from the left side or from the right side, and which carbon-carbon bond are you considering, right? So this is my back carbon, this is my front carbon. So then I need to decide, will I draw it? What do I start with? Start with what's in plane of the paper, right? The groups that are a straight line are in plane of the paper. Dashes and wedges are either behind you, behind the plane of the paper and away from you, or in front of the plane of the paper and towards you. All right, so if you're looking at it from the left side, that methyl group is in plane of the paper and is pointing upwards. If you look at the back carbon, there's a methyl in plane of the paper and is pointing downwards. So I'm going to start with the back carbon. I'm going to choose this because the group pointing in plane of the paper is pointing downwards. All right, so that's my back carbon. The group that's in plane of the paper is pointing downwards. And then I have my dashes and my wedges, all right, either to my left or to my right. And if I look at my front carbon, then the group pointing in plane of the paper is pointing upwards. And then I have my dashes and my wedges to either side, okay? So now, always helps to start with those, right? This is a methyl and this is a methyl. So if it helps you to go in and put a CH3, do so. If you keep it, we're drawing it as a line bond structure, so it does reflect a methyl or a CH3, right? So I'm just going to go ahead and erase it. If you ever think it's a hydrogen atom, right? If you only see three groups on paper, the fourth one has to be a hydrogen. So if any of those groups are ever a hydrogen, you have to write in the hydrogen. Otherwise, it reflects a carbon atom. Okay, now, so let's take a look. So suppose you're looking at it from the left side, right? And you have the dash that is pointing behind the plane of the paper or the screen and the wedge that is pointing towards you, right? And in front of the screen or the plane of the paper. So if you're looking at it from the left, is the dash pointing towards your left hand or pointing towards your right hand, right? Is it pointing away from you or towards you? Yes, it's pointing away from you. And you should have noticed that it's pointing to your left, right? So then OH on my front carbon is to my left. That means bromine must be to my right, and whatever is in plane of the paper is pointing upwards. And then if I look at the back carbon, the dashes are going to be on the same side of the Newman projection. The wedges are going to be on the same side. So it looks like both my alcohol groups are on dashes, so they're both to my left. And chlorine and bromine are both on wedges, and they're both to the right, right? So that's what we refer to as a Newman projection, right? What happens if I rotate? What happens if you rotate, the front carbon by 60 degrees, right? Those groups are going to overlap. Right, so we're going to consider that. We're going to consider the different conformations when we're looking at Newman projections. I'm going to go ahead and erase that. Okay, so we're going to erase that. We're going to go back and look at butane. Right? So let's take a look at this butane. And suppose we're looking down this carbon-carbon bond, right? Actually, so suppose we're looking at it this way, right? And here's the way we're looking at it. Right? We're looking at it down this carbon-carbon bond. Okay, so you have two hydrogens, right? This carbon is attached to two groups. There are two more groups, and those two groups are hydrogens, because if carbon has two bonds on paper, it must have two more. They're hydrogen. One is going to be a dash, and one is going to be a wedge. So we're looking down this carbon-carbon bond. So our front carbon, the group that's in plane of the paper, is pointing upwards. So, pointing upwards. It's a methyl. It's attached to two hydrogens, so I have to put in my hydrogens, right? My dashes and wedges are the hydrogens. And then my back carbon, okay, and then my back carbon, this is my back carbon, right? My back carbon, we have a methyl, and the methyl is pointing downwards, right? This circle is really my back carbon, and the methyl is pointing downwards, I still have 2 hydrogens, right? You can't keep it as a carbon. You can't not draw the hydrogen because it means what you have is a carbon atom. All right, so draw in your hydrogens. All right, so that's what we have. So now imagine you rotate this molecule, right? So this is what we have. Those 2 methyl groups are on opposite end. And if I rotate the molecule by 180 degrees, those 2 methyl groups are going to be on the same side when we're looking at it down a carbon-carbon bond, right? But we're looking at it down a carbon-carbon bond. So I will rotate. I'm going to keep my back carbon the same. All right, and I'm rotating my front one and rotating it 180 degrees. So now my front carbon right, is kind of overlapped the methyl with the back methyl, right? So they're exactly on the same side if you're looking down that carbon-carbon bond. So if you think about, and if I go in and once again and I rotate it 180 degrees, I'm going to go back to my original, how it originally looked like, right? Think about it that you're taking it and you're rotating it once again. Well, we could think about it in terms of the overall energy as we rotate, right? So we could think about it in terms of the potential energy associated with that rotation, right? So would you expect it, and if you recall, potential energies associated with the position of something or with the conformation, right? Think about it in terms of the steric interactions. Those 2 groups are bulky. Would they prefer to be on that same side, right? Or there could be some steric clash or interaction between them? Or would they prefer to be as far apart as possible, right? Okay, so which one would you expect to have higher energy, right? When they're kind of overlapping. So potential energy increases. So it makes this molecule slightly less stable or higher in energy, right? If we draw it, this could be our anti-conformation. This is our different conformation. And all we did here is a 180-degree rotation, right? And if we rotate another 180 degrees, then that we're going from these 2 groups being as far apart as possible, or if you think about it, they're anti to each other. They're what we call an anti-conformation. They're as far apart as possible, basically. They're 180 degrees, not Celsius. They're 180 degrees, right? And if we rotate 180 degrees, then we're at a different conformation. And when those 2 bulky groups are kind of right on the same side, overlapping, we call that eclipsed conformation, right? So we're going from an anti-conformation to an eclipsed conformation, and at the end we're going to end up having an anti-conformation once again. But what if you rotate 60 degrees in between, right? Then you'll get what we call a gauche conformation. So does each molecule only have a single gauche, a single anti, and a single eclipse conformation? No. Think about it as that 60-degree rotation, right? Think about it as they're anti to one another, okay? And then you're rotating 60 degrees. They're gouged to one another. That's 60-degree angle apart. They're apart by 60 degrees. Another 60-degree rotation, another 60-degree rotation, and at that point you're at 180, so they're eclipsed. You know, the difference is really 0 degrees, whether you're looking at this group, this group, this group, or both groups, and then you can rotate once again. 60 degrees and another 60 degrees and another 60 degrees, and then you're back at 180, or an anti-conformation. So you can have multiple gauche and eclipse conformation, and you'll have anti-conformation as well. So all it is rotation around that carbon-carbon sigma bond or single bond. Those are 60 degrees apart. Okay, so how do you decide? I mean, in this example, are we looking at the alcohol groups? Are we looking at the two methyls? Are we looking at the halogens? How do we decide which structure is more stable when we have a more complex molecule? We look for the bulkiest groups. We want the bulkiest groups within a molecule to be anti to one another, and then that would be the more stable conformation. All right, I hope this was helpful.